I'm not gonna say we're back anymore.
Hi everyone, we're back.
And hi Theo, it's very nice to join us.
Hey, how are you?
We're great. We're actually excited for your talk because, as we promised people yesterday, we're gonna have mixed subjects, architecture and design, and yeah, now it's one of them. It's about design, and it's about patterns in Python, which is I never wrote a line of code in Python. To my shame, I have to say that. We have Vlad here to counter that, but
Okay.
yeah, it's been rising in popularity over the last years.
Yeah, it's a very nice language. So it's used a lot in a lot of projects. So if I remember correctly, Google actually, when it started, its main programming languages were Java and Python. And YouTube uses Python, Instagram uses Python, Reddit uses Python. So there are a lot of big companies using Python, and its usage varies from scripts that you have for DevOps or stuff like that to big web applications or desktop applications or machine learning or data science. So yeah, it's a very nice language.
So yeah, now is the right time. Maybe I should take a closer look. Right?
Yeah, definitely. So this I think this session would be a good start because
I'm all ears. So that yeah,
right.
we can we're gonna regroup afterwards to chat and maybe ask some more
Yep.
questions. Now you have the floor.
All right. So let me share my screen. Okay. 1 second. Make this full screen. Right. So welcome everyone to Design Patterns in the Python world. In this session, I want to explore a little bit how Python's philosophy and language lab features impact the way we think about, we implement, and we use design patterns. As a target audience, I hope it's for any developers any developer who has some Python interest and wrote some code. It would be great if you have some experience with Python and also know about some design patterns, but that's not mandatory. If you are an expert both with Python and with design patterns, I'm not sure you'll find out new information. So anyway, the session will start pretty light, but it will get a little bit complex by the end, and I'll have a lot of code. So, if you're watching this on a small screen, it will be nice if you go full screen. All right. So in the next couple of minutes, I'll briefly talk about me and my Python journey so far. We'll have a general overview of design patterns, and then we'll have a look on some scenarios and patterns in Python. So, okay, I'm a software developer. I started with Java and C++. I also worked with other programming languages and technologies. And in the past 7 years, I worked with Python. And I remember my first interaction with Python. I was in high school and I had a dual boot computer with Windows XP and Ubuntu. And I didn't have disk space for Ubuntu, and I wanted to install some packages, and I decided to remove some packages, and one of those packages was Python. And there was a warning there that there are some packages are depending on Python, and those packages will be removed as well. And I was actually pretty happy because more packages removed, more space for me. And I didn't read the whole list of packages, and in my defense, it was alphabetical list. So Ubuntu Base and Ubuntu Desktop were like the last two packages in that list, so I didn't get a chance to read that. So I proceeded with removing Python and restarted my computer, and I broke it. Nothing else worked. I had to reinstall Ubuntu operating system again from scratch. So yeah, it was not a very good day for science, but I understood that Python is not just some scripting language that you just use for small utility script, but that it's actually pretty widely used. And yeah, so years later, I started actually working with Python. So I wrote some Python code, and I remember that initially the code looked very weird. Like I said, I was coming from Java and C++, and in Python there was no getters and setters, no access modifiers. So you didn't have to have a main class or main method or whatever. I usually had fewer import statements in my code. I instantiated classes, but there was no new keyword, so no stuff like that. So the general feeling was not doing serious programming. So, but I continued with that because it just worked. So yeah, there was something about Python, and this made me continue to look for Python projects and work on Python projects. I think about worked on 10 projects in the last 7 years, mostly web applications, RESTful APIs, both microservices and monoliths, with multiprocessing, multi-threading, also async IO. I started new projects and I joined existing projects, and I've noticed something. And regarding design patterns in Python, fewer people talk about them. There seem to be fewer design patterns in code. For some of them, the implementation is really simple. And for others, the Python language or standard library provide an implementation. So I started looking for these things on the internet. I read some articles, some blog posts, watched some videos from Python conferences and so on. And the general idea is that indeed, there are some built-in language features which are pretty cool and replace some design patterns. Then perhaps you are using some frameworks, and those frameworks provide some patterns. And another thing is that we tend to avoid big applications. Sure, there are big applications written in Python, but most of us work on smaller applications. So that's why perhaps we don't work with those those many design patterns. So I also think that the Python philosophy, which is presented by the Zen of Python by Tim Peters, I also think that this philosophy and writing Pythonic code also influences how we think about design patterns, how we implement them, and how we use them. Here are only some lines from the 19 ideas of the Zen of Python. Now, when I say design patterns, I'm actually referring only to these ones from this book, Design Patterns, Elements of Reusable Object-Oriented Software. It's written by Eric Gamma and others. It's an old book, 1994 or 95. And yeah, the authors are known as the Gang of Four. What is a pattern? A pattern is something that you did in the past, it was successful and can be applied to multiple situations. A pattern is not invented, but is discovered, and this is very important. So a software design pattern is a general reusable solution to a commonly occurring problem within a given context in software design. Before jumping in, I want to discuss some criticism regarding design patterns. I have 3 examples here. The primary one is that some design patterns are workarounds for missing features in some programming languages. And I partially agree with this, and hopefully we'll explore some features that Python have and other programming languages don't have. So that's why some design patterns we won't see that often in Python. Another criticism is that with design patterns, you kind of write a lot of code that does nothing, but in a pompous way. And if you implemented design patterns in other programming languages like C++ or Java, because of those design patterns, you had to add a lot of interfaces and abstract classes and code that really doesn't do anything regarding to your business domain. So yeah, I kind of agree with this criticism too. And the third one is from Paul Graham. It's more broad what he says here, because it's not regarding only design patterns, but any kind of patterns in the code. And he says that this is a sign that we're using abstractions that aren't powerful enough. And in this presentation, we will use some powerful abstractions. So, perhaps this design pattern criticism applies in some programming languages and less in Python. Now, with all these criticism, we still use design patterns. And when we use design patterns, when we implement them, we follow some principles. To program to an interface, not an implementation, and to favor object composition over class inheritance. So let's see how are these principles applied in Python. Well, regarding the first one, to program to an interface, not an implementation, Python uses duck typing. Duck typing basically means if you're looking at something and it looks like a duck and it quacks like a duck and it walks like a duck, perhaps it's a duck, so use it as a duck. So in this little example here, we want to save some data to an output stream, but we don't enforce that. We just need something, we'll call it out, that has a write method on it. So basically don't define the type for your variables, for your function arguments, or for your function return values. So this language feature means that the first design principle is always applied. Regarding the second design principle, to favor object composition over inheritance, it's very easy in Python to do this. It's very easy to write a wrapper. So I have this little example here. If you have an object that you want to wrap, you create another class called wrapper. In the constructor, you receive the wrapped object, and you define a magic method. In Python, there are some protocols that the Python follows, and one of these protocols is called getAtter. So if you have a method which starts with double underscores and ends with double underscores, it's called double underscore method or dunder method, and this getAtter method is called whenever Python tries to do some lookup for an attribute, so a field or a method, and that method doesn't exist on your instance. So it gives you a chance to do this lookup yourself. And in this little example, what we want to do is to delegate the attribute lookup to the wrapped object. How do we use this wrapper? Well, here I created an object called items, which is an empty list. I create another object by wrapping the original one. And when I'm printing what wrapped items.append is, we can see that after the lookup, Python knows that append is a method on the list object, not on the wrapped object. So when I call append on the wrapped items, it actually calls append on the original wrapped object, on the original list. This is very easy. If we didn't have such a powerful mechanism, we would either have to inherit from list in order to have all those other methods, or we would have to implement all those methods by ourselves and on each method to call the corresponding method from the wrapped object. All right, so let's look at some scenarios. And the first one would be the Singleton pattern. So let's imagine you're writing a class called screen. It has some methods such as set background, which receives some image as an argument. And now people are using this screen of yours by creating instances of the screen. And you're staying and with the code in front of you and say, well, I have a laptop with one screen. I have a phone with one screen. My tablet only has one screen. So I think it's a good idea that in my program, there's only one instance of the screen class to be created. And this is called a singleton. So how do you implement a singleton in Python? Well, please don't. I'm pretty sure that in most cases don't actually need a singleton. And this will introduce a global state, and this will make things harder to test. But if you really want to have a singleton, my personal preference is to use a factory, because your object, in this case, your screen class, will still have one responsibility doing what the screen does, and you decouple the responsibility of creating one instance to another, to a factory. In other programming languages, we have a syntax for object instantiation and another syntax for function call. So this means that whenever you create a class, perhaps you need to take some time and think, okay, do I want people to actually use the class directly or to use it via a factory? In Python, there is no separate syntax for object instantiation. So for example, if we look at this line, we can't tell if example is a class that gets instantiated or is a function that gets to be called. So it's easy to start with a regular class and its constructor. Okay, in this case, result equals example is object instantiation. And then later, we can rename the original example class, and we can define a function called example. This function may have some arguments and may have some logic, And at the end, it will return an instance of the class. The calling code is the same, result equals example. So it's a function call. The original call is unchanged. We didn't introduce any backward incompatible changes. So how do we implement a singleton with a factory? Well, on the left side, we have the old code. So it's a screen class, and this is the usage. And on the right side, what we did is to rename the screen class and to add a global variable, and then to add a function which is called screen. And this function will handle this instantiation of only one screen, and it will return that only instance. We can see that the calling code is the same. So this is my preferred method if you really have to write a singleton. It's not the only way, there are multiple ways. And the main drawbacks for this one is that people who are trying to extend their screen class won't be able to do that. And if they're doing type checking or instance checking, that will also fail. But for most common cases, this works. So let's continue with our example. We discovered that it was actually a big mistake to have a singleton. Everyone else actually uses laptops connected to other screens or to video projectors. They can stream videos from their phone to their TV. So they actually have multiple screens. So our users want multiple support for multiple screens. Well, no big deal. We keep our screen function, so our factory. We keep our original screen class. We may add other classes if needed. So for example, a wide screen or a big screen or whatever. As you can see, they don't have to be in the same hierarchy. They don't have to extend each other. They can be separate objects. So our screen factory will decide which kind of instance do we need. The old code, which would just call screen, would still work. And the new code would pass this argument in order to get a wide screen. So this is another language feature of Python, which is default values for arguments. So if you don't supply an argument, it will have a default value. So we had a look on two language features: no separate syntax for object instantiation and default argument values. And the benefits of these language features are rapid development and iterative design. We're going to look on another scenario, adapter pattern. So let's imagine that we are using a wallpaper library. This provides us a wallpaper class, which has width and height properties and a draw method. And this wallpaper library also provides us a today's wallpaper function, which will now select some wallpaper and create an instance of it. And let's also assume we are using a screen library. And this screen library has a screen class with a set background method. And this method uses an image and calls a resolution property on that image, and also calls the paint method on the same image. The problem we are facing is that we would like to use these two libraries. We would like to use the screen and to get today's wallpaper and set it a desktop background. If we try to do that directly, we will have an error because the wallpaper doesn't have those attributes, resolution and later paint method. So how do we do that? Is to use an adapter. An adapter allows the interface on an existing class to be used as another interface. No, but the inner functionality should be the same, right? So how do we do that in Python? We will use the code that we introduced in the beginning regarding the wrapper. So an adapter will wrap the original wallpaper, will define a new property called the resolution, and this will be, in our case, let's say a tuple with the width and height of the original wallpaper. And we'll have a method called paint. And this method will just call wallpaper.draw. Again, we see this dunder method, double underscore method for getAttr, because we don't know how this wallpaper adapter will be used. And we want every method lookup and attribute lookup to be delegated to the actual wallpaper. So in order to use this adapter, we still use the original screen. We get an image with today's wallpaper function, and we create a new object called adapted image. And this will just use the wallpaper adapter that we just created. And now when we call screen.setBackground, we will just use this adapted image. And this works. And this is how we implement it usually in other programming languages. With the distinction that with this getAther, it's simpler to use to implement a wrapper. But still, if we go back to this slide, it's a lot of code, and all we need is a resolution and a paint method. So is there a way to improve this? And in Python, there is a better way to do that. So instead of creating the wallpaper adapter class and using it, we can actually define attributes on the fly on objects. So I have the image object, and I define a new attribute called resolution, which is a tuple with the width and height of the original image. And I can also define a new attribute called paint, which is a function that we just call image.draw. Just a remark, it would be possible to say image.paint equals image.draw, but it's safer to do it with a lambda, in my opinion, because usually we don't get away with methods that have different names, but we also have different arguments or different argument orders and so on. So if you have a lambda, then you can call the other method with other arguments or in a different order. So yeah, we can now use the existing image that we have fetched for setting the screen background. The advantage here is that if later we would have used this image, sending it to other methods, it would still carry these properties that we have just defined on it. So we've seen these language features, getAther, which helps implementing wrappers, and dynamic attributes, which is also called monkey patching. And it's really easy to adapt objects. So I think that that's one of the reasons that we don't hear a lot of Python developers talking about, hey, today I wrote an adapter or things like that, because you do this on the fly almost without noticing it. And if you've done any web development in Python, for example, I'm pretty sure that quite often you had some sort of authentication mechanism that would just take the original request and set a request.user on it, even though the original request obviously didn't have a user property. All right, so moving to scenario number 3, which is the iterator pattern. Again, we have this wallpaper library, and this wallpaper library defines a choose wallpaper function. So you give it some images, and it has a nice algorithm. It checks if that image is a natural landscape, and if that image matches the current season, so it's autumn, and it returns the first image that it found. So you have image collection that's pretty big. You perhaps store it in a database or something like that, and you want to use this choose wallpaper function. Let's imagine that we are using some sort of library, and we have this load images function, and what it does is create an empty list of images, connect to the database, execute some query, and for each of those results, for each of those rows, it appends a wallpaper to this list. Then closes the connection and returns that images list. So how you write the code? Well, you call load images, and then wallpaper is choose wallpaper from that list. But you have millions of images, so you are using a lot of memory, and it takes some time because you have to load all those images. And this is a well-known problem with a well-known solution, and you find it pretty early on with Python, because in this case you don't actually have to create a list. When you have a for loop in Python, it's actually a for each loop, right? Compared to C++, C++, or JavaScript or so on, this is a for each loop. And what it does behind the scene is something similar to this. So it calls iter on the items, and this returns an iterator. Then it has a loop, and in this loop, it calls next on the iterator to get the next item. And it does this up until there is a stop iteration exception. And when that happens, the loop is stopped. So corresponding to this function, iter and next, there are some methods. So Python has multiple ways of dealing with this kind of situations, multiple protocols, and this would be the iterator protocol. So when you call iter on an object, it calls underscore underscore iter underscore underscore, which is dunder iter, and then the iterator must have a next method on it. So in this example, if we would have to rewrite it with an iterator, we can have a item collection class. The constructor can have a list of items and the initial position, and it will have to define an iter method that should return an iterator. Now, it can be its own iterator, so it will return itself. And then, as an iterator, it will have to define this next method, which will basically see if there is any items to return, and it will return. And if we exhausted the initial list of items, it will raise a stop iteration. So how do we continue to do this with our images? Let's create an images.db class, and we will speed the original logic that we had in that load images function in these methods. So let's assume that when we want to create this images database, we will actually connect to the database and execute the query. This will make sure that it fails fast. So if there is no database or the query fails or stuff like that, it will fail from the beginning. Then we define iter method that returns itself. So we will be our own iterator. And then when next is called on this iterator, what it does on every next call is to fetch one row from the database. If there is no row, then if there is a row, then it will create the corresponding wallpaper object with that data. If not, it will close the connection and raise stop iterations because there are no more images to get from the database. So yeah, this is nice. I'm pretty sure that you've heard about the iterator pattern from other programming languages, and this works. It's a very good implementation, but there is a lot of boilerplate, right? Every time we have to write a new iterator that does something slightly similar but a little bit different, we still have to implement all these methods and do all this stuff. And also, the logic is expressed, all over these methods, and you have to take care of when you're opening the connection, when you're closing the connection, and so on. So, is there a better way to do that in Python? And the answer is yes. Python has generator functions. It's a convenient shortcut to build iterators, and you do that by using the yield keyword. So this is the original function, load images, that we will start from. As we can see, what's wrong with this is that it has this list of images. It depends on this list, and then it returns everything from the beginning. So we will get rid of this images list, and then we will replace this append with yield. So every time we have a new result, we yield it back to the caller. So this is how we transform the original load images code to a generator function. The logic is clear and natural, and the implementation is similar to the original one. So, but it doesn't build that list in memory. And the memory usage of this function is similar to the iterator. So we don't have to accumulate a lot of images in memory. We don't have to wait up until the whole process is done. We can yield, with each row from the database, we can yield a new wallpaper up until that function that we are calling actually stops the iteration. So with this third scenario, we have analyzed these language features. Iter, next, and stop iteration, which define the iterator protocol, and yield, which is for generator functions. And the benefits is that the main benefit is that it's really easy to implement or generate an iterator. All right, so yeah, in this presentation, I think I covered that this Python's philosophy and language level features impact the usage, implementation, and thinking about design patterns. I'm quite surprised that it took less than expected. I usually spend more time when going through code. So yeah, this will be it. And if you want, we can go through several sections from the presentation if needed.
Thank you, Theo. We do have a couple of questions. First off, I wanted to ask, is there such a pattern that you go back to time and time again? Something that you use almost daily?
Well, yeah, from the list that I presented, and this is why I chose them, is that these kind of patterns are used on a daily basis, and because you use them so often, you don't notice that there are some design patterns because they're kind of usual. So it's very common in Python to do this trick with switching from a class to a function, and that function might return the same an instance of that class or an instance of another class. So this is pretty common. Also, the iterator pattern is built in Python, so to speak. It's something that you learn from the beginning because if you come from C++, for example, or C++, and you're used with iterating with I variable, right, over a list of items, you see that you don't do that in Python, and you understand that there's an iterable there and there's an iterator, and you find out about this iterator protocol, and yeah, you also use this on a daily basis without thinking too much about it, and without going home and talking with your wife or with your friends. How did you do it? Well, today, well, it was a nice day. I implemented the iterator pattern. Well, no, it's something that you just do. It's not something that you brag about, right? And yeah, so that's why I've chosen these patterns, because you might use them on a daily basis and without being aware that you're using some design pattern or something like that. And as a Python developer, after some time, if you don't go back to other programming languages, so if you don't go back to writing Java, for example, you forgot about these nice things that you have in Python, right? Or if you go to C++, if you don't go to C++ and you still write Python on a daily basis, you forgot about how nice it is. So up until you go back and say, okay, I missed this feature from Python, and it's way easier to yield values from a for and stuff like that.
That's why I use C#, but yeah, I'm guessing the Java guys. Sorry.
No, another thing that's very nice is that programming languages tend to use stuff that they see in other programming languages, and this is pretty nice because we've seen that some features that were available only on Python or on C# are now available in other programming languages as well. So yeah.
Sorry, I was just
just
promoting a question. A question just came up, so it's rather interesting. It was saying that you kind of covered a part of this question when talking about the criticism. But some people believe that design patterns are useful not only at the micro level in the applications, I'm assuming iterator or stuff like that, but oh no. Some people believe that design patterns are useful, but only at the micro level in the application. They do not dictate the way in which the application is developed. What is your take on this?
Well, it depends on the patterns that you are using, right? So there are some design patterns that also dictate the way that your whole application will look like. But there's a thin line there, because perhaps they're not necessarily only design patterns, but more of architectural patterns also, and so on. But for example, if you look at the state design pattern, or your program is a state machine, right? Well, this kind of dictates on how your program will look like, right? Or if you're using, for example, a memento, or a strategy or stuff like that, right? It also defines the way that certain parts of your program will look like and will behave like. Yeah,
of course, it makes sense that
but after some point, those are not necessarily design patterns, because yes, indeed, in some cases they're more micro level, and after some level, we are talking about more than how you structure some classes or some behavior, but how the code will look like and how it will shape your code. So this will go, I think, from design patterns to architectural patterns. So if you're talking like MVC or stuff like that.
There's also different books. So
oh yeah,
the design pattern book, and also the enterprise architectural patterns, which is different level.
Exactly.
But yeah, you're totally right. I wanted to ask, what's your opinion on type annotations in Python? Do you use them?
I was part of a project that used them, but it was something so it was more of a framework, and in order to be sure that things are going right, we used type annotations. I don't usually use type annotation, so in most of the cases, no. Because I really like the idea of duck typing, and I really like the idea of not enforcing a certain type as a function argument, for example. And this kind of leads to some nice things, actually, because I've seen that in Python, variable names and function names are way more descriptive, are way better than in other programming languages. Because in another programming language, you can be lazy. If you have a certain integer and you have to pass it to a function, it will be I, right? But in Python, you have to give it a meaningful name. It has to be age or width or height or something, or time spent or something like that, right? And because you don't have this safety net of static typing, what I've seen in Python projects usually is that there are more tests than in other programming languages, because you have to be sure that your function arguments is what you are expecting, and you have to cover all these cases and so on. So yeah, it's an interesting trade-off. It allows you to be to do rapid development, to do iterative design, and to write code faster, and but it also leads to better names and cleaner code, in my opinion, and also better practices, like I said, with testing. And I've also done test-driven development, and Python is the only language that I was able to do that. And I think that this is also because of duck typing. You can start writing tests and call methods on objects, even though the objects don't have the method yet, right? So then you loop and implement the method and other functionality and so on. But what's your take on it?
I come from a strong C# background, so I make everything. You learn a language and you write that language using. I could write C# using assembler, so I kind of write C# in Python. So I'm using type annotations. I totally get what you're saying, and not binding a type to a certain. Not binding a variable to a certain type has a lot of advantages. I'm an autocomplete kind of guy, so I just like the idea to know what I want to say and to put it there. So that for me means I need to use type annotations, unfortunately.
Yeah, but if you have a look, of course, in C# and of course, and also in Java, both languages try to borrow a little bit of this. So you can now use type inference, and you don't declare the type of variables, and Yeah.
And C# we've had that for years.
Yeah.
It's not a contest, Vlad.
For me, everything is, I'm a developer. I like numbers and I like to make them go up. Everything's a contest. We have another question from the audience though. Python is nowadays a language used in a lot of environments. So it's web, enterprise, DevOps, machine learning, etc. And are the practices you mentioned applicable to all of those environments, or could you suggest some that, for example, work more in ML versus web?
Yeah, that's a good question actually. So indeed, Python, it's used from simple scripts to web applications, desktop applications, smaller ones, bigger ones, and also to machine learning and data science and so on. And like I also said in the presentation, luckily most of us work on projects that are well focused. So kind of follow the Unix philosophy. So if it's an utility script, it only does one thing, or it's a background job, it only covers some domain, or a web application, perhaps it's more towards a service or microservice or stuff like that, right? But if your code base is very big and your team is bigger, or it's a project across multiple teams, I think that it's good to have some some good practices. From the examples that I presented, I think that most of them can be applied because you're not actually doing anything magic, right? You're providing some better ways, and you can move on. Perhaps this is also related with your previous question with the type annotations. So I assume that if you have like a really big project with a big team, type annotations might also help, but I'm not sure. I wasn't part of any huge projects with huge teams in Python. So yeah, some of these patterns, I think they still apply. They don't actually do anything wrong. So if you're familiar with Ruby, for example, Ruby has the idea of open classes. So if you have a string class, you can define a method in some library that will be used on the string class, or there's the open function in Ruby, and there is some library that if you import it, now open function suddenly can open FTP connections, and it just works. And you might get used with that. And I think C# has similar functionality. So you have an existing string class, and you have you want a new function on it, and you just define it, and people will be used with that. And then when you move to another project, they don't have that functionality, right? Python doesn't have this kind of magic. So even if you have these things like ways to patch objects, and stuff like that, it's not the same sort of magic, because those patches are not magically applied when you import a library. They are applied when you actually call a function, or you actually do it on demand. So yeah, I think these patterns that I presented, are things that you do on a day-by-day basis in Python, and you don't think about it, regarding the adapter, regarding the iterator, also regarding the factory. So for these particular ones, yes, I think they can be used with no problem. For others, yeah, I think we can use various tools to be sure that the whole team uses the same practices.
Yeah, just make sure everybody's on the same page and the code looks the same, even if it's written by the different people.
Yeah.
I think we have got time for one last final question.
Yeah, there's a new question. So do you prefer mocking or patching, or using DI and fake objects?
It depends on what kind of project are you working on. So if you're doing stuff like domain-driven design, so if your classes are very well written and they're kind of separated, then you can use the actual classes. You don't have to mock anything, because you can actually, for unit testing, for example, right? you can instantiate the class, test the logic on it, and stuff like that, because that class is not connected to anything else. But if you're doing web development, for example, with Django, it's pretty difficult to have this decoupling, because if you're using Django database and ORM and model, these are tightly coupled together. So by default, in your unit test, you actually connect to an actual database and see that everything works. And you can use some mocking libraries. So, for example, mock to mock this kind of behavior. So, if you really want to write tests that don't actually connect to a database or don't actually call network resources and so on. So, if this question was about only testing, unit testing.
Yeah, I'm assuming that's what it looks like.
Yeah.
So, it was. All right. Well, I think we reached our break in the sky.
Right.
Thank you so much, though.
Thank you very much.
Yeah, and I learned a couple of things. So
Okay.
thank you for that. Well, even Dan learned a couple of things.
Tomorrow.
So looking forward to hearing more of your talks at the next events.
Yeah, me too.
Thanks again. And well, we're going to take a short break. See you all in 14 minutes this time.